It's on? Yeah, okay. May I start? What's sitting? Yeah? It's okay? May I start? Okay, yeah. So, hello everyone. I'm Mathieu Courne, so I'm professor in Paris, and it's my pleasure to be here to share this deep learning session with Professor Eduardo today. So, actually, I was giving a talk yesterday, something more oriented on the type of research work we do in my lab. But okay, of course, there are some strong connection with the course of today and the different points that Eduardo introduced this morning. So I just wanted to come back to a few things about architectures, deep architecture, and in particular for computer vision that I mentioned yesterday, and that is exactly, the point where Eduardo stopped it, this morning about the discussion. So let me jump to exactly this point. Yeah, okay, this morning. So typically, Eduardo introduced this morning this kind of deep convolutional architectures, and one very important step was, in 2012, when exactly this architecture proposed by Hinton team for the main competition for a large-scale image classification have been won thanks to, so typically this kind of deep architecture, okay? And as mentioned by Eduardo this morning, it was like a huge gap in performances between that architecture and all previous, I would say, handmade computer vision style architecture that were proposed for this task up to this time. All right. And so one of the question about this architecture and then this modeling and is can we do better? Is it from 2012 after? The question was, is it possible again to improve and how? And typically there were some questions this morning about, for instance, the depth of this system. So is it better to go to a deeper architecture? Is it better to go to a wider architecture? I keep the same number of layers, but I'm going to add a lot of new filter. So that means typically the wider, it means that instead of using 96 filters in my system, I'm going to try with 100, with 200 filters, okay? And the other point, of course, is the size, exactly the size of these features. So this is certainly the second main important parameters. And the third one is about the depth, okay, of this system, right? And yesterday I was also mentioning many things about having this kind of trade-off between the spatial size of your deep architecture. Here you see that when you go through the system, you step by step, you are going to reduce this kind of spatial sizes, all right? And then up to having no more spatial information. So that means at what point you will get like only one big vector. And then you can continue the process by having exactly as MLP we saw this morning, and it's exactly this last part that we call the fully connected layers, okay? But as I highlighted yesterday, and I really pointed out, it's really an open question to keep as much as possible some spatial information into the deep architecture in order to, of course, to better at least detect, understand, especially having more spatial information and so on into the deep. Okay, so from that point, I mean, there are three main architectures that have been proposed by researchers during the last few years. And the first one has been proposed by the visual group of Zisserman in the University of Oxford, so the VGG. And as you can see, I mean, there are many different characteristics, but one point is that it's twice deeper than the previous one, okay? So you have much more layers into that architecture. And the other point, very important, is also that it's quite a bigger architecture, because then you have more than 100 of millions of parameters into that system. Okay, for a practical point of view, it's also very important to see where are most of the parameters inside that system. Okay, so what I mean is that you can have like something like 10 levels here. Okay, as soon as there are convolutional layers, the cost is very cheap in terms of weights, number of weights that you have. Okay, the most important part, so the most number of parameters that you will find in this kind of system is when you have a fully connected layer in between, for instance, for one input, 1,000, or let's say 10,000 as input, and you want to go to the next layer that has also 10,000 neurons. Sorry. So that means that if it is a fully connected, okay, layer, so that means you are going to have 10,000 times 10,000 parameters just on this layer. Okay, so that means it's 100 of millions of parameters just for one layer. Okay, and typically, if you take the VGG architecture, you will see that certainly most of, it's not certainly, I mean it is that most of the parameters, I think like something like 80 millions of parameters are concentrated on the first fully connected layers that you have here. Okay? All right. And so, from that step, there are also, I would say, two kinds of variation, two different, things that differ a little bit from the direct, straightforward, deep architecture, convolutional pooling, fully connected. It's just when you consider, so it has been proposed by Google Brain team, this kind of things. And it's just the question of instead of having one way, I mean, the just one way to do your convolutional layers, you are going to consider, I mean, 2 or 3 parallel computation of different convolutional layers, filtering, okay? And then you put them together, you concatenate, or you have some pooling step, and you go up to the next step here. Okay. Okay, and except that make a little, sometimes few difference here. You see that you go through all the dip up to the end of this dip. Okay, and so it's not very. It's still, I mean, in the same vein as before, except again that it's very. I mean, it's a very deep. Convolutional net here. We have up to 22 layers on that. Okay. Okay. They also introduce some kind of tricks about the learning. Okay. Eduardo give them the main step for learning by backpropagation on this kind of architecture. Okay. So I should mention that one of the main problems is the gradient vanishing. So that means that you, when you want to update one parameter here, you know that you start to update the parameter here, and anyway you have to compute a gradient here and then from that gradient to go to the layer before and to compute the gradient, and then to back propagate all these kind of things. And so you can have somehow the way that the update that you try to do is going smaller and smaller and smaller, and so at the end of the day, when you arrive close to this kind of earliest layers, you don't have anything to for update, okay? No more information. And so they try also to modify the classical learning just by saying, okay, I want to have my loss function at the top of my deep system, but also I put some auxiliary function, okay, of cost here. So I have two new branches where I say, okay, I also want to evaluate the cost here, okay? Exactly as if I would consider much less deep architecture, okay, but just for training. So it's just some kind of auxiliary cause just to help and just to avoid gradient vanishing, okay? So people really tried a lot of tricks like that just to help for learning, okay? Okay, so that was the second one, and actually at the moment the most famous one and the most used for computer vision stuff is based on the ResNet, what you call the residual network. Okay, so it's a very deep net. Okay, they propose several versions from 50 to 200 layers. Okay. And the main difference, okay, so you see one example here of the 152 layers, okay, and there are just one difference that is yeah, quite interesting difference is that you have like this kind of what we call a skip connection that you have many times inside your deep architecture, okay. So what is exactly a a skip connection? It is a way that, and this is, okay, I put a zoom on this here, but it's exactly what you see also many times here, okay? And the point is that you just connect the input of the layer straight to the output of the next layer, okay? And the idea is that the deep and what you learn, what is inside here, I mean this layer, so all the weights that you're trying to learn are somewhere here with a hollow function, for instance, for nonlinearity, and then a second small weight layer that is convolutional, both of them. Then actually you try to concentrate here not exactly on the filtering of the image, but on the filtering of a residue between the input and the output, or between the output and the input. Okay, so really to be able to model many details. So that was the first step. Okay, so to get rid of the main, I would say, of the main shape, and to be able to focus on really small difference and small things into the signal. But the second way that they motivate this of course, this new connection is really for learning, and this is really, I mean, like against the vanishing, okay? Because when you back propagate the gradients, then you go through that branch, but also, okay, you propagate the gradient here, so you don't lose anything at this step, okay? All right. So, and at the end of the day, it's quite less. Even it's very deep. Okay, they have less parameter than, for instance, the VGG architecture I presented before. Okay, so I skipped this kind of again very recent. I mean, like not even will be presented next month about how we can, of course, combine the skip connection idea with multi-parallel convolutional layers, both putting them together, and so proposing no more ResNet, but ResNext. Okay? All right, so that was just to continue on the yes, if any question. No. Yes, okay, yeah. Yeah. Okay. So the question is that is it comparable to, for instance, autoencoder, right? So let me again put the right slide. Okay. And the answer is no, because actually it's still, I mean, it's still something completely feed forward. I mean, you have the input here, okay, and sometimes you just skip to the next layer, okay, but the point is here, what you try to do is you try to go from the image to the label, okay, so you really try to go from your input data up to the high-level semantical label that you want to have in classification, for instance, or for also for. Yes. Okay. Yeah. Yeah. Yes, yes, okay. So, yeah, well, what does it mean exactly? Yeah, it's exactly, it means exactly what you say. So that means that sometimes we just allow the input to go straight. I mean, as identity, I mean, we give it also to the output of this layer. Of course, at the end of the day, we have no more, I mean, the X from here is not available here. I mean, okay, that's sure that even if you have some jump and some skip connection and many different skip connection during the dip, of course, at the end of the day, what you have available is really something like completely different than the input, so image, okay? But it's just a question of being able sometimes not to concentrate on straightly transform the image, but only trying to focus on something that is like, let's say, the image minus the difference, or the image minus the transformation that you consider, and so on. Okay? So it's really, I mean, what we have here is that we try to learn something. If you see the output, the current output here, okay, the good thing is that, okay, what is learned here, that is F, is exactly this Y, okay, minus X, okay? So you really, I mean, say to this part of the dip, okay, try to model, okay, X minus Y in the most efficient way with convolutional, okay? Okay, was there a question about, I would say that this is my main comments on type of architectures that we consider now that are deep, very deep in the feed-forward case, okay? In the second part of my talk today, I will talk about other kind of architecture that are no more feed-forward, okay, but that have some recurrent connection. And this is another story. But for the really, I mean, like straightforward and feed-forward architectures, okay, we have, yes, basically from 2012 up to now, I mean, we see that have been emerged, that's three kind of architecture, okay. And for the rest, I mean, it's, as mentioned by Eduardo this morning, you still have, even if it's an end-to-end learning, actually, you still have to fix by hand the number of features, the size of the number of layers that you consider, and the size of each convolutional layers. Okay, it's still something like, okay, you can try to optimize them on, of course, on validation state. You have some stuff about Bayesian hyperparameter optimization, or you can also derive some kind of tricky architecture that try to switch from a certain number of layers to more layers, but okay, it's still very, I mean, like ongoing work, okay? Okay. So, if there is no question about, no more question or the question about classification, okay, I'm going now to say, okay, all of us now at least knows more or less how we can process the ImageNet dataset, so the famous one mentioned this morning with more than 1 million images. So you can take some pre-trained architecture, architecture that have been trained on that dataset, okay? And so it can be VGG, for instance, okay? You have pre-trained models available, so you can just download the pre-trained model. You can do that with VGG. You can do that, of course, with GoogleNet, Inception, V1, V2, V3, okay? They are available, right? Okay, so you can download that. Also ResNet 1, okay? And the question is that, is it possible to use that architecture? So, I mean, there's image representation plus classification to do other things, okay? I mean, different things that just doing the task of ImageNet, okay? The ImageNet task is that if I give you one image to that system, okay, it will give you the answer among 1,000 of possible answers, okay? So if you want to use that system for your personal fun, okay, you can download the system and you just take a picture, you present this picture to the system, and it will give you an answer up to the 1,000 of classes that he knows, right? Okay. But okay, for people doing, for instance, specific tasks in computer vision, that can be, for instance, working on robotics stuff, where you have a mobile robot that need to recognize a different place, or if you are working on medical images, or if you are working on a specific, for instance, fashion type of images, and you want to know if you can take benefit of this kind of pre-trained architecture just to apply to your data set or your type of images. For instance, you know that you have many dresses, okay? And you have 100 of classes of different dress, okay? And you want the system now to be able to automatically recognize which kind of dress, which kind of creator is it, and so on, okay? And so, I think Eduardo briefly mentioned that before. You can really, I mean, like, use this as a pure transfer. So, okay, you don't modify anything. You just cut the head, of course, of your net, because you are no more interested in having like the 1,000 classification of ImageNet, okay? But you just keep like the layer before, okay? And you have, by this way, a very nice and very generic image descriptor, okay? So it's like an image feature, okay, for zero cost, okay? You just take the pre-trained architecture and you pass your image through this deep, okay? And you just get the head of the deep and you keep the last vector, okay, coming out from the deep, all right? And with that vector, you can do, for instance, it's what I present here, you can do retrieval. So I have a bunch, I have a big data set, a very large data set of fashion images, okay? I use my deep, I present each image to the deep, okay? I take the vector representing each of that image as the output of the deep, okay? And then after, I just do, thanks to a query, I retrieve the most similar vectors in my data set. Okay? Does it make sense? Yeah. Right. And so, for instance, if I present that image, okay, I have in a used data set, here you have the most similar images that I can find from my data set, just using my deep without training anything, okay, except using the pre-trained, for instance, the VGG deep architecture, okay, and after doing like a very simple, similar search to the query, okay, like a classical content-based image retrieval stuff, right? So what you see also, and that have been mentioned also by Eduardo, is that when you get to that description, it's already a very semantical description of the content. So that means it's not just like Eduardo showed at the first layer where you just detect something like a corner, an age or things like that, a blob on some things. But when you go up through and you go up to the end of the network, you have something like that is very semantic, okay? So thanks to this very semantic description, you are able to retrieve and to make some very, useful semantical stuff, okay? All right, and then you can also use, if you have a classification task, for instance, you know that you have some, for instance, what I put, something like many medical images with two classes, melanome, for instance, benign and malignant melanomes, okay? Two types of images. You have training data, okay? You can say, okay, I just use my feature coming from the deep. I don't do anything more, and I use a classical classifier. For instance, it can be a tree-based, it can be a SVM-based classifier, whatever you want, and you can just train your the top, I would say the top of the system on that, and then you will get very nice results on small data sets. Okay. As Eduardo also mentioned, if you prefer, you can just say, okay, I add a new layer, okay, from randomly initialized, okay, and I'm going to do fine-tuning of this of the network, okay, but I only fine-tune. I tune. Actually, I train only the last layer, okay. I keep frozen all the feature before, right? So you have like your very big deep from VGG or GoogleNet, and then you add a last layer, and you train only that last layer, okay, to for your target classification task, right? And it's also possible to say, okay, why not fine-tuning the whole architecture thanks to my target data set, right? It's possible, but you have to pay attention to that and to do it carefully, because if you just do like backpropagation without taking care on the way that you tune and the parameter of your last layer and all the parameter from your deep, okay, you just risk to remove all the what have been trained on ImageNet before, okay? So what you need to obtain, if you don't pay attention to this kind of details during your training, is that you are going exactly as if you were training your big architecture from scratch, okay, for your target application. And that is not a good idea. Okay, do you have any idea why it's not a good idea to say, okay, I just take my VGG architecture or my Google architecture, right? I cut the head, I just put, like my two classes layers at the top, and I train to learn my whole architecture from scratch on my target data set with my label melanome images. Why it's absolutely not a good idea? It depends, but okay. Okay. Okay, I say it again because, yeah, I think I lost everyone. Sorry about that. Okay. So, yeah. Okay. To make this point very clear, okay, what I'm saying is that, okay, this type of architecture, as you see, you put the image, you go through like your large convolutional up to here where you are, okay, straight to a fully connected layers, okay, and here, as you can see, this is the output. So it's exactly here the output that you, corresponding to the task, you try to optimize your deep net, okay. So that means if it's ImageNet, you have something like 1,000 neurons here, okay? Because usually when you try this kind of deep architecture, the output is 1 neuron per class, okay? So you put 1 neuron per class, you have 1,000 of classes in your problem. Then you train, thanks to the whole ImageNet data set, okay, your whole system. So that means you tune all the parameters here, okay? The good news is that people already did it for you and for me, okay? So we can pre-train their parameter, okay? And then what we do, because we have a specific target classification task, okay? What we do is that I do melanoma classification. So here I remove this last layer and I put a new layer with only 2 neurons, okay, for cancer type or not, okay? And then for that I have images, okay, let's say 1 or 2,000 of images for both modalities, okay? And so my point is that I use my system, so my pre-trained parameter, you go from one image, you go up to this here, okay? And you don't tune anything here, so that means you have like a large vector, 4,000 of coefficient. That is a description of your melanoma image, okay? And this description here is like one big vector is going through an additional layer, okay, with 2 outputs, right? And what I said previously is that we can train, okay, this last layer, okay, without changing anything before, right? Okay? So it's just I'm going to tune like a very flat, okay, 1 layer net, okay, or as I mentioned before, you can take a SVM, you can take a tree, whatever you want for classification, right? But if you take a neural net, okay, you can keep the same kind of idea, architecture, so that means 1 linear transformation plus, for instance, 1 ReLU nonlinear function, rectifying linear unit function, okay? And then you go up to the output, right? And so my question is that if I do back propagation, okay, just to tune this last layer, right, okay, then why not doing back propagation through the whole net, okay? And this is called fine-tuning, okay? So you have a pre-trained architecture, you add a new layer, of course randomly initialized, from scratch, and then you try to, of course, completely learn the last layer, because it's a new one, and fine-tune all the parameters of your VGG or AlexNet DeepNet, okay? Fine-tune on your target task, okay? And so my question was, is it possible and is it a good idea to say, okay, I just keep this type of architecture because I know that it's very good for ImageNet, okay? But now I'm going to learn from scratch. I'm not using the pre-trained architecture. I'm just randomly, I keep the structure, but I randomly initialize all my weights, and I try to learn from scratch. Okay? Do you think it's possible, and do you think it's a good idea? Any idea about that? Yeah. Exactly. Okay. So there is a question of the size of the data set. Okay, as mentioned by Eduardo this morning, when you do deep, okay, usually if your deep is really deep, and then if of course he has a lot of parameters, okay, if you train this system on a very small data set, training set, okay, let's say for instance if you have only few hundreds of data set that you have the label for your melanoma problems, okay? So that means you try to find a function, okay, that fits, remember this morning, it's just like a big function with many parameters that you try to fit, okay, to pass from some input points where you know the decision function, okay, where you know the output, and you try to find the best function to pass through this data, okay? If you have only 3 data, remember the blue dot points of Eduardo this morning, and you have like some model that with the order of the model is m is equal to 100, you are going to learn something that is overfitting over your data, okay? So what does it mean here? It means that for my melanoma example from my training set, okay, for each of the melanoma, the answer will be problem or not problem, okay? I will be able to perfectly fit over this training set, I mean, with zero error, of course, because my system here is so huge, so I can tune, I can close my eyes and try many like that. I will have no error, okay? But when I am going to present a new image, the answer will be as random, okay? It doesn't learn anything, actually, of the underlying structure of your problem. Okay, remember the small sinusoid? This is the underlying shape of the problem, okay? And you learn something that makes, okay, a mess of things, okay? All right? Okay. So that's why you have to first, usually if your data set is very small, do not train from scratch, okay? Use a pre-trained architecture, first message. Second message, if you do fine-tuning, do it carefully. Pay attention on the way that you fine-tune the parameter. Because if you authorize to modify too much, the risk is that you are going to reverse the training that you did before. So it's exactly if you come back to some like randomly initialized weights, okay? So usually what people do is that you have no more only one learning rate as presented this morning. When you update your gradient, you have a learning rate, okay, to say how big your gradient update may be, okay? When you do that, you have one, of course, learning rate for your last layer, okay, randomly initialized, and then you back propagate with a second weight decay that is usually much smaller than the previous one. So that means you authorize to modify, but very few, the parameter of your system, okay, of your deep. All right. So okay, let me come back to that. I can't remember. Yeah, okay. All right, and so okay, this is the first way, okay, to be a smart user of deep systems, okay, all right? Just pay attention to that, take care, use it as feature extractor, and then fine-tune or not, and decide depending on your problem. You can also use that to do clustering, for instance, of course, even if your target task is not classification, you can exploit the meaningful characteristic of the high-level feature that you have to do retrieval, to do clustering, to do many different tasks. All right? Okay. If you want to go one step further, okay, this is typically, the kind of things I presented yesterday, is that you have to think a little bit more on which type of data this kind of big architecture for vision have been trained, okay? And what I mean by that is that ImageNet that's true is a huge data set containing many different kind of data, but all of them are always very well prepared. You have to think about that. It's 1 million images that have been seen by at least 3 people, okay? Just to say what is in the image, and eventually, to define the kind of images and to reject some images that are not typically with only one object, well-centered, and so on. So actually, even if it seems very, general and very big data set, you have a lot of work that have been done, like pre-processing of the data set to propose the ImageNet corpus for learning, okay? And for sure, on your data set, on your problem, the things may be quite less well-defined, okay? So that means typically, if you are processing like street images, okay, usually you don't have only one big well-centered car, okay? You can have several cars, and you can have, not only one, but you can have also cluttered, you can have different objects, etc., etc. All right? Okay, so typically there are many ways to tackle this kind of problem. I presented some of the work that we did in my team, in my group, with some of my PhD students on that, and to pay attention about how to localize the information during the classification, right? And see, this is usually, connected to the weekly supervised learning, right? Okay, but what I'm going to explain today is a little bit different, and it's connecting now no more to the classification task, okay, but how we can do localization and how we can do detection of objects thanks to this kind of deep architecture or deep style architecture. Okay. Okay. So in computer vision, usually we have three kinds of works, so classification, of course, and we like also the detection. I'm going to talk about that. And the third one coming late after is also to be able to segment the images. So to be, up to the detail of the pixel at the pixel level inside the image. All right. Okay. So this is example of some results but also you can imagine some kind of ground truth also that you can have. So it depends. Sometimes it's results. Sometimes it's ground truth of just to show you what we expect to have when we work on detection, typically. So that means that we are able. You see here, we have many objects, or here 2 objects. We are able to detect the sky and the person, or here the clock, and here the bed, and so on. So the main idea is to go into the image, okay, and to be able to find a bounding box that is around okay, the object that interests you, okay? So if I have the big picture of the many different tasks that you can have, as I mentioned before, this would be, I mean, like for that input in a classification problem, I expect to get the label. So let's say cat here, right? Okay, so I'm going to present now a few things about having more than cat, okay? Still for, in a classification context, so that means that during my training I just know the label, okay? But I try to infer the label plus some information about where is located the cat inside my image, okay? This is for a single object. After I can go through up to multiple objects, as presented before. So then the idea here it can be, and the color is given for different classes, okay, to be able to find one dog in blue, okay, two different cats in red, and a duck, for instance, in green, right? And of course, then if you want not having just like a bounding box, but be able to go up to the shape of the different object, okay, usually it's called segmentation. And when you separate the different object, okay, by instance, okay, it's called instance segmentation. Okay, so for localization, first, briefly, I mean, like explain how it works. So just to remember, here you have C classes, right? So your input is one image, the output is a class label, and usually you evaluate how good is your system by counting how many times on a test set you give the right answer. I mean, the system gives the right answer. Okay, if you want to have the localization, you add, okay, this kind of bounding box, okay, and so that means you are also able to predict, okay, as well the label, so the cat, but also the distance. I mean the bounding box on something like, for instance, 1 point, and of course the width and the height of the window, right? So, and this is. I mentioned that because this is also very important modification of the classical work that we do with deep, right? And here we are going to modify the architecture, and I'm going to explain how, okay? But because we start to have like a bicephal output. So we have no more only one branch, okay, as output, but we can consider two branches, okay, one for classification and one for regression to regress the bounding box, okay? And when we do that for this we are going to consider a neural net to be able to express this kind of bounding box here that could be 4 numbers, and of course when it's a fully trained data set, you also have the bounding boxes during the training, so you are able to compute directly a loss function between the 4 numbers that you produce by your deep and the ground truth given by the training set. Okay? So typically, if I go forward, the kind of how I can learn this kind of deep architecture, okay? I'm considering as previously AlexNet, VGG, whatever you want, okay? So you go through that, you have this kind of final convolutional feature map here, okay? Up to the fully connected, for instance, of the VGG, up to your, then it's classical classification stuff, as I mentioned, okay, with pre-train and transfer for the top of the deep architecture. And then when it's learned, okay, you consider now a second step where you are going to plug, okay, a new part, that exactly this part, like a second head of your deep net, okay, just to be able to learn actually the prediction, okay. So you are going to do like a regression on the head, for instance, or on that, in order to be able to produce, okay, of course, on the first branch, the classification label, okay, that you find here, and also certainly the best, what you try to predict is the best bounded box having this object, okay? And so that the things that's quite new in the recent years is that you have, you share part of the deep, okay? So all the first step, okay, so all of several layers, and in particular usually many convolutional layers in your deep are shared as well by the regression, as well by the classification branch. Okay? All right. So when you add, of course, you can train this kind in this system also by using the L2 loss here. Okay? This is the first step, and after with the fourth one, okay, you are in test, everything is learned, okay, and then you are able to predict, okay, as well the label as the bounding box, okay. So that, of course, there is one subtlety that is you can decide eventually that you are going to predict one box per class, okay, or be agnostic to the type of classes and just say, okay, whatever the class of the object, I think that the object is there, right? Okay, so, and you can do it for multiple side objects, right? So, okay, this idea is very useful, okay, and I've been practiced a lot, okay. I'm now mention a second strategy that allow you another point that is very important is to be is that to allow to use a deep net whatever the size of the input is. Okay, so in the structure I presented here, okay, it's good to have like a prediction of the bounding box, but okay, as I use VGG, okay, the size of the input is fixed by my pre-trained model, right? And you can change that, you can adapt in order to be able, okay, to fit with other kind of images than 221 by 221, okay? With the VGG, you have this fixed size of the input, okay, and most of the time it's like that, okay, except if you change or consider some modification into the deep. I'm going to explain now, okay? And that was also the kind of techniques I presented yesterday in the weekly supervised learning stuff, okay? But, okay, what does it mean? It means that for an input that is my dog, my cat, okay, with this size, okay, I have one output. If I just have a bigger image, okay, so that means that I can present, okay, several sub-window of size 221 by 221, okay, to the net, and then get the output with the bounding box regression, okay. So I can repeat actually this kind of things, and then I will get several different output. Okay, as many as I will be able to extract some window from my new input image that is larger than the first one. Okay, so that means that, for example, for this image, I will be able to produce, let's say, 4 different classes score. Okay, for having a cat, and I can merge them together. Okay, just by this kind of things. Okay. To produce like okay, a base score, a merging base score for this classification, and also to merge all the bounding boxes to get only one. Okay. Okay, all right. Okay, so how it works in practice on the larger images? You see, if you have like this image with a bear, okay, the idea is that this image may be very large, okay. And then you are going to consider some window of size 222 by 222, and you pass through, and for each of them, you will get one answer, okay, plus the bounding box, okay? And then you do it going through like a sliding window up to your very large image, okay? You can do it at different scale. It's what you see here. I mean, you rescale the image, you can, and in many different things, and then you can apply exactly the thing I presented before, generate all the bounding boxes, and merge them all together at the end to get only one, for instance, one, and certainly the best bounding box corresponding to the object you are looking for, okay? But of course, this is not efficient in terms of computation, okay, because imagine, for instance, here, if I generate, let's say, 10 different sub-window, and here, perhaps 100 of sub-window, that means I need to go through 100 of times through my net, through my deep net, okay, because I have to present it, all the images to my net, okay? So it's absolutely not efficient in terms of computation to do that. Okay, so to process one image, I'm obliged to go perhaps 200 times through a deep net. Okay, and of course you can modify this kind of things, and this is certainly also one of the very interesting things that have been proposed recently to modify the deep convolutional architecture, okay? And I would say that it's very important for computer vision, but not only. I mean, all the type of data that you process, as soon as you have the convolutional layer available, or that makes sense to use in your stuff for natural language processing, for text processing, and so on, that now you see a lot of convolutional working with impressive result on that. Okay, you are aware to having a data that have not the same length. Okay, it can be the things when you process sentences, when you process documents and things like that. Okay, and so the way that you change the point of view is that you just consider what you have before. It was like the fully connected layer here. You reconsider this fully connected layer as a 5x5 convolution. Okay, with actually the 4,000 different filters. Okay, so it's really, I mean, like just like a trick, okay, but it's very very efficient, because then you are able to process a larger image. Okay, let me show on that example what is a larger image. Imagine that is exactly the image of the cat here, okay? If you have a larger image, so that means you have like this yellow part here, okay? So your input is larger, okay, here, right? When you go through convolutional subsampling here, okay, you obtain with just this kind of convolutional, at the end, a one by one, okay, one result. If you do exactly the same kind of process, convolutional, okay, as Eduardo presented this morning, so a convolution, that means I apply a filter of size, for instance, 5x5, and I go through my whole image, exactly as Eduardo made the moving things this morning, okay? And then when you do that, no problem, you can compute, okay, as the image is larger, okay, the answer will be larger, but it's exactly the same work. Huh? And the parameter that you have learned already with VGG is still there, and you can just apply, okay, your larger CNN here. And it's the same after with that one, so you obtain this, and just the difference is that now your output is no more of size 1x1, okay, is size 2x2 here, right? And it's over, okay? So, yeah, exactly, okay, so I mean, you get all these kind of things, you put all them together, and then, of course, at the end of the day, if you have a 2x2, okay, you finally pull them, all of them, by, for instance, doing the max score, taking the max score that you find over the 4 different scores that you will have. Right? Okay? Okay, all right. So I think this is the main things for localization. Let me finish by recalling this kind of localization. Yeah, okay. Yeah, it's just to mention that Eduardo explained that, I mean, it was like the deep revolution in 2012 for classification. It was not at the same time the same for localization, typically, but 1 or 2 layers after, it would have been the same. Okay, so the same train of having deep and working with deep. Okay, was first attempt was for the classification, and the year after coming from localization. Okay, so and detection. Okay. All right. So, okay, I'm going now to go up to this the second things. After localization, I'm going to go on detection, and typically I'm going to just to give you an overview of the best techniques actually to do that. Okay, so the best deep architecture dealing with this problem of detection, right? Okay. So, of course, you can try to apply the techniques I just presented before, okay? Having this kind of landing window with location and trying just to evaluate with the bounding box regression as I mentioned before, okay? But of course, even if you have this kind of nice convolutional interpretation of the fully connected layers, okay, you still have a lot of problem by having a huge number of possibility of different ages and different size and shape of the object that you can find in the images, okay? So that's why one of the main techniques to tackle this problem, okay, so to be able to, for one input like that, to find that there is a, for instance, a dog and a cat, and to localize and to detect, so I mean to put the bounding box really, I mean, like close to do that. The idea was first, okay, I don't want to consider like all the sub-window with all the shape and asking the system in a certain way if there is an object and which object is there, okay? I'm going to just to cut this complexity by pre-process my images, okay? So that means that for each image, I'm going to just in a class agnostic way to say, I give you like 1,000 of regions. That should be the best example for having the object. Okay, so like the first step will be, I mean, from one image to have this kind of proposition. I don't say they are correct, okay, but I give you that to now process in a deep way. Okay, so for people used to do computer vision, I mean, this is a very, I mean, like a classic way to consider a problem is to say, okay, I don't want to take or to pay attention to the whole complexity. I want first try to read off some evident things that it can be, it do not have to be considered later. Okay, so I first cut and just say, really focus, okay, pay attention on these areas, and that's all, okay? All right, so there have many propositions to do that recently. I mean, how from one image to be able to propose several bounded box that make sense, okay? Okay, so something like that here. Okay. Of course, there is a question where you can to do it in a fully unsupervised way. So I mean, you do not consider that you have some bounding boxes as output just to be able to fit something. No. Most commonly, people actually do, for instance, like in this algorithm selective search, where you consider a different level of segmentation, okay, basic segmentation of your image, and then you try to remove, I mean, some inconsistent region and to get, I mean, the most significant with a size sufficiently consistent with your problem and so on. So there is a lot of tricks, okay, but at the end of the day, you are able to propose something like 2,000 regions as candidate for being an object I'm looking for. Okay. So it's exactly what is summarized here at the bottom of this layer from Gershik. Okay. So your input image is there, and then you have the first step I just presented, where you have the region of interest that have been proposed by, as I mentioned, the selective search algorithm. Okay. So that means for the deep, you are not considering all the images at the beginning, but only those images. You rescale all these images, and you go up to a convnet, right? Okay. So if you go into the detail, I'm going to go fast on that, but okay. Then so that means that for your in that case, okay, exactly as I mentioned before, you are going to consider here like for this kind of things, you are going to consider the pre-train, okay, from ImageNet, for instance, AlexNet, okay. They cut, okay, they remove this, okay, and they reinitialize, of course, the layer here, okay, and they now consider only the 20 classes plus the background that they have in the target data set where they try to train their system, okay. Okay, so after you can consider some extraction of the feature, and then trying not to exactly to learn. As I mentioned, you can learn a neural net, but if you prefer, you can also really train a detector, so a binary detector for each of the class. For instance, I want to know when I present an image if there is a cat or not. Okay, and this is the way that I'm going to evaluate my data after. So I really want to learn a binary classifier for class for the class cat. Okay, and so in that case, I'm going to consider all the features from coming and presented a cat. Okay, so here there are all positive examples for cat, and then after I have plenty of examples in my data set that are not cat. Okay, and I'm going to train a binary. If I come back to the sorry. Well, okay. I'm going to then to learn this kind of binary SVM on the top of my deep. Okay. But okay, there are plenty of ways to do that. They started to do that at the beginning, and after, of course, for the second part, you also have the regression. Okay. So as I mentioned, exactly as before, you have the classification branch, and then you add a regression branch in order to okay, yes, sorry, I come back to the architecture. Where is, right, here, okay. So you have this second branch to be able also to say, this is that object, and this object is inside this bounding box, okay? So actually, as you already have, of course, an input bounding box, okay, the question could be, is it very important? This is just to refine, actually, this position, okay? Because when you go through and you really recognize a kind of object, you also can be interesting in refining the initial bounding box that have been extracted first by the selective search, okay? So it's just like a post-processing to refine the way that you find that object, okay? Sorry. Okay. But Okay, this is the main architecture. So I think that was proposed in 2015, certainly by Gierschik. So just I think that guy at that moment was in PhD or in postdoc in Berkeley, so in University of Berkeley. And then he's now in the Facebook artificial lab that is called FAIR. Okay, so this is a worldwide artificial intelligence lab of Facebook. Okay, thanks to certainly this work that he proposed. All right. Okay, and but okay, in the first proposition, there was a certain number of flow. So of course it was very slow at test time. Okay, of course, because you need still to go through the test time for all the different net for each of the proposition, exactly as I mentioned in the previous localization step. So we can do better for that, of course. And of course, SVM is not end-to-end learning, so we don't like it in the deep community. Okay, and of course, we also have, as I mentioned, a complex multi-stage training pipeline. You go first to learn the deep, after you put the SVM, after you put the regression, so it's many stuff. Okay, so of course they propose to fix all this problem. Okay, so this is called the fast RCNN. Okay, the first one was CNN for, of course, convolution neural net. The R was for region-based. Okay, so region CNN, and the fast because it's faster than the RCNN. Okay. All right. So it's exactly the same idea I presented, where you convert all the fully connected layers into a convolutional layers. Okay, and then actually you are able to process whatever the size of the image on this kind of convolutional once. Okay, so you compute that once, and then you do your work about the region proposal here. Okay, at this step. All right, so it's better integrated also because it's no more like I do a selective search that has nothing to see with my deep. It's really inside the deep architecture where you have like some first auxiliary task here to be able to generate. And then you go through, of course, the same fully connected layers for all of them, and etc. Okay, so I'm going to skip the detail on how it works. There are many details that is very important if you need to do this kind of things. But for sure, it's quite it's much more faster. Okay, even if it's you have like 10 times faster, certainly, and it started to be reasonable for processing not online but very fastly. I mean, images in text. Okay. All right, and so certainly, yeah, there is a last consideration about going still faster, okay, and really, I mean, like having this kind of region proposal inside in a deep consideration, in a deep architecture, and then this will give you the faster RCNN. Okay, so finally, okay, okay, it's over for this. This is the whole things for this kind of fast and faster. So RCNN, fast RCNN, and faster RCNN. Okay, and all the code for that are typically available. So you can download the code from different kind of library, but certainly from Café. Okay, from the Café library to do that. Okay, and to summarize, okay, this is really, I mean, the main idea was from one image, okay, I can more or less with different kind of strategy extract region and to go through a classification and to be able to classify and also to say where is exactly the object inside the image, okay? So that was really, I mean, like the main things for detection with RCNN, and this is really, I mean, the way that you can modify the RCNN to be fast on faster RCNN by globally integrating all the different tasks into the deep convolutional neural net. Okay, and as I mentioned, one really very important things that are exciting people and in the community at the moment is really, I mean, like having something with no more one head or eventually two heads with two different tasks, okay, but a multitask consideration. So I can consider that I have a classification problem, and then a second problem where it's really, I mean, a detection problem, and a third one where I can consider some kind of regression, so for some type of images. And one of the idea is to capitalize a maximum of the things and of the learning together, okay? So try to share, I mean, a certain number of early layers, okay, the first layers up to a certain point, and then after, okay, you go through with one image, and for that image where you have a classification problem, then you turn into the classification dedicated branch, okay? But if you have a regression problem, then you go through the same, okay, the same shared layers, okay, up to a certain point where you go then on the right to the dedicated branch for regression, okay? But of course, the idea is that if you share some part of the architecture, it's very good news for having perhaps not so many data for learning, okay? Because you have, you take advantage of the different objective where you have different training sets that will play all together for the first part of your deep architecture, okay? So I mean, for part of the problem, you put all the things, all the tasks together, and then after you diverge, right? At a certain point, right? Okay. Okay, so that was some of the things I presented yesterday. I'm not going to come back to this detail, but some work that you can consider also for classification and localization in a weekly supervised way. Okay, so all the slides will be available for the different talks. So, yeah. You want to okay, do the break now? Yeah, of course. Just before segmentation. So this is segmentation. Okay, just to keep your attention for after the break. Okay, we will see now really, I mean, like how to get these kind of things. All right. Thank you very much, and see you after the break. So I'm going to continue and to finish on this part, purely visual part, I would say, visual consideration, and then I will switch to other kind of deep net that are able to process also some other kind of data like sequential data, temporal data, and so on. Okay, so just to finish on this kind of ImageNet problem or related to ImageNet, classification, segmentation, and so on. Okay, let's say a word about segmentation. So as you see here, the goal is a little bit different, but of course correlated to the first one is to be able to eventually localize, but in a very precise way in that case, because you go up to the pixel level in order to be able to identify the different objects that you have in the scene, and it can be all the object or not. Okay, you see the difference with traditional segmentation is usually that you just try to put them together into regions, the pixel of your image in a fully agnostic way without any class consideration or things like that. In this kind of semantic segmentation or semantical segmentation or things like that, and in particular doing that with deep, the idea is really, I mean, like I want to train a system to segment, okay, and of course, with this segmentation, having the label corresponding to each region, so to each pixel inside the image, okay? So there is, I mean, I would say certainly two kind of approaches to do that. You have that one. I'm going to explain a little bit more after, but basically you try to go through a dip and then you try to go through a deconvolutional dip, okay? So convolutional, that you're trying to reduce the size eventually to get some kind of fully connected part. And then after you try to reconstruct in a second part of the dip all the spatial information in order to have this kind of things, this kind of mask or deep mask at the end of the day, okay? But typically, I mean, in the case I mentioned, so when we are doing multi-class, typically image classification, the goal is typically like that. So I have this kind of image as input, and I'm going to give some color for each of the pixel of the image, okay? Except that sometimes I can consider that if it's not an object that I'm interested in, okay, I can have this kind of big background class, okay? And of course, it can be something like that where you try just to recognize, I mean, like the type of object, for instance, a chair, okay? But you can also go further and try to have an instance-based recognition. So that means you are also able to say this is one chair and here this is another chair, okay? So it depends on the consideration you have. And in the instance-based, of course, typically here the ground truth would have been 3 different objects corresponding to 3 different chairs, and then it's instance-based classification. Okay, so the first type of method is, as I mentioned, this kind of things, okay, where you try to convolution, deconvolution, okay, and the other one, and certainly the most practical one, is again something that where you try to get some convolutional style, always convolutional style of a first dip, pre-train on whatever you want, okay, and trying to exploit then some kind of spatial information that you still have at the top of your net, okay. So remember, for instance, with ImageNet, when I presented this kind of images, I will get something with, cat, for instance, for one cat, I will get only one score, yes or not, is it a tabby cat, okay? If I go through my convolutional stuff and so on, as I explained before, okay, for this kind of larger images, so that means I am able more or less to have this kind of output, okay, where here I am able to, for a tabby cat, to produce a map, okay, that tell me for a different point that could be not exactly a pixel because it's coarse than a pixel, but let's say that each point here corresponds to a small set, I mean, like a group of pixels here, telling me how I am confident that is a tabby cat. Okay, so this kind of heat map, okay, for coming from each class, okay, and those people really, I mean, like recently, I mean, I think, yeah, it's got here, but it's something like a CVPR last year, was proposing this kind of consideration, okay, so convolutional style of deep to keep some spatial information from the input inside the deep, and exploiting, of course, this kind of heat map that I'm able to produce. So I mean, like now for any kind of input I'm going to produce, as you see, it's not exactly the same size as the input, but I am able to produce some kind of heat map score, okay, some score that are coarsely, but that are localized in my input image. And then I have like extrapolation operation, okay, like for instance, bilinear interpolation, or B-spline interpolation, whatever you want, just to be able from that map to come back to the size of the beginning, okay? And then from that, I can start to have like the classical work that we do for classification. That is like for segmentation, like it's CRF. So you try to classify the thing thanks to it's a category of Markov field to be able to classify, taking into account, or to classify each pixel, taking into account the way that the neighborhood is classified also. Okay, some kind of Markov model style that you can have. And one of them very useful for image segmentation and well known is a fully connected CRF, conditional random field techniques. Okay, so that means actually each pixel is connected to all others. But there are some ways and there are some very nice and fast techniques to solve this kind of random field, okay? In order to get what you perhaps you see or not, I don't know, in the back of the room, but some classification for in that case plane and background. Okay, so here, basically, the help of deep actually is to be able to produce here some kind of very useful and very semantics feature, okay, coming in as an input, as a descriptor for each of the pixels of the CRF, okay. Okay, that was donc certainly the first way to consider the problem, and then the other one is try also okay to take advantage again on the deep convolutional neural net, okay. But in that case, as we do not have any more spatial information. When we are on the top of the convolution, on the head of the convolutional neural net, okay, we add some mirror neural net, okay, and we can also, I mean, like have some connection, or to enforce some connection in between the convolutional side and the other side. And typically, what that authors, that Escola did was when you decide when you decide to do a max pooling, so when you decide that this is one pixel that gets this max pooling, you keep the information, you keep it in memory, and you keep it for having the deconvolutional on the other side. So when you then go from 1 pixel to 4, okay, you keep for each image how did you merge the information, taking, for instance, the first one on the top or left, okay? If you did that when you compress, when you decide your max, you keep the information, and when you have to come back from 1 to 4, okay, you will extrapolate this information to the one that won the competition during the feed-forward step, okay? But actually, okay, we made many tests on that, and it's not so important, so crucial to have this kind of things. You can extrapolate, and the main important things, of course, is to learn the filters here. Here, I say that we have like a deconvolutional layers, but concretely, I mean, like here, you still have like some convolutional filter that you learn, okay? So you have this kind of putting 1 to 4 value, and then convolutional layer, and then again extrapolate, and so on, okay? And there's all these filters are also learned in the same way, thanks, of course, to a new specific to the pixel-based segmentation loss that you have at the top of this operation, okay, of this neural net. Okay, so when you arrive here, when you are in a fully convolutional segmentation, you are able to process a loss for each pixel, okay? You have a score for each pixel here, and you can compare to the segmentation maps that are available during the training when you are in a fully convolutional work, okay, framework, right? Okay, and see here, typically I show you how this kind of, okay, so it is not the right image. It should be here the bicycle images that have been presented, but when you presented some bicycle images, you go through that, and then after here, I think this is something like one of the maps that I obtained 7 by 7, perhaps 14 by 14 here, okay? And my point is that from that map, I have to extend, okay, to a new map that one. So there are different ways, and as I say, different ways to do that. This kind of extrapolation. Here, you just, okay, pick one of them, and you are going to choose in between 2 by 2 where you put this value, okay? And the other value are null. That's why you see here, I mean, like what is null is like in this blue background color, okay? So from that, just by extrapolation, I get like a new image that is exactly, I mean, the image, the first one here, okay? And then I go through one layer of convolutional with filters, okay? That's why you see you have this kind of densification and smoothing of the different things, and it's like if we complete all the missing information in that one, so we get something like quite denser, okay, and smooth, also smoother. And again here, okay, so you go through a certain number, and then after you have to again to upscale, okay, and in that case, you, again, you are going to look for how you downscale for each of one, and you redo the same thing. So that means you extrapolate one of these value up to 2 by 2, okay? So you choose the one that I want during the feed-forward step. Okay, and as you can see, you redo it a certain number of times, and at the end of the day, you will have some mask with the two whales of that started to be clear here, the two wheels of the bicycles and so on. Okay? All right, that's basically how it works. So, okay, one can notice that it's cool, but it's very expensive for training. Okay? So if I need to train on a new data set, so that means you have by hand, okay, to segment, okay, all the objects for all the images that you have in your training set if you want to have like a fully supervised image segmentation, right? Okay, and even if there are, I mean, some data set available now, okay, they are not very huge, okay, and it's difficult for them to go full scale. I mean, to scale this kind of techniques because always it's too costly to have many data for training. Okay. So, okay, one way is to get rid of these very accurate, fully segmented images and try to say, okay, this is very cheap to just have some labels at the image level. Okay, so one of the questions, and this is really, I mean, the question of the weakly supervised image segmentation context, is that can we get rid of having on giving to the machine during the training each pixel labels, but can we just say in one image, as before, I know that of course, I have the background, and I have some chair, and I have one table, okay? So instead of providing during the training this kind of very, like a pixel-based segmentation, I just give some few information about the different labels. Of course, it's quite much harder to train, okay? So why it is very harder, or why it's a very hard problem for learning, it's because you can't evaluate, okay, the output of your system as we did before, because we have no more this information, okay? As I mentioned, if you try to learn this kind of system, you go through your convolutional, deconvolutional, you go up to the output, okay? You have a map, okay? But then you would expect to be able then to evaluate the error pixel by pixel, okay? But the system only tell you, hey, okay, there is a background, there is a chair, and there is a table, and it's over, okay? You have to do with this information, all right? Okay, so without going into the detail of this kind of techniques, the one way to do that is okay, very, very simple and basic idea, but really successful techniques, okay, is actually, yes, to consider, exactly as before, the fully connected part here, okay? So I have my image, the convolutional neural net. In that case, it's not the convolutional, deconvolutional. This is the other kind of techniques where you have the fully convolutional ones with this kind of maps as the output, okay, that go into the CRF after. But okay, this map, you are going to produce a loss, okay? So in fully supervised, you have the data to compute the loss, okay? It's given at the pixel level. When you don't have it, you use this kind of bias to produce, okay, so what you can see here, not very well, but actually you are going to have like a second task that you generate yourself, exactly the mask. Actually here there is 3 regions. We don't see very well at the screen. There is 3 regions, okay, corresponding to a mask that is produced by the system, by our system automatically, okay? So we use a score, some score produced at a certain level of the deep convolutional, and we bias this by this label information that we have during the learning. So we exploit this kind of information. We know that there is a cat. We don't know where, but this will produce actually the map where we are quite confident that this cat, this person, and these things are, okay? So we have this kind of step to produce this map, and once we have produced this map, of course, we can use this map as a ground truth to compute our loss, okay? And then from that ground truth and that loss, we can backpropagate onto the system. So, of course, there is some kind of tricky things here, is that, okay, we use a loss produced by our system to train our system. So, you know, it's something that we have to pay attention. It can diverge or converge on something that is not interesting. So, usually you have like this kind of 2-step that are well separated in order to produce the map with one side, and you produce many maps that are not perfect, but thanks to this map, when you try and use this map to refine the deep learning, you will get a stronger deep neural net, okay? So during this second step, you fine-tune to get your stronger neural nets, and then you stop this second step, and you come back to first step, that is to produce, all the new maps that should be better because your deep is better now, okay? And so you have this kind of alternate optimization scheme, okay, that allow you actually to mimic the fully convolutional neural net framework. All right? Okay, so some results typically produced by my colleague Li Kuhn, ou Lequin in French, because it's a French guy working for, at the head of the Frere lab, but also professor in the New York University. So they produce some kind of very, amazing segmentation results last year. To be able to, even for very, fuzzy kind of things they are able to detect. So there are plenty of objects with clutter, but okay, the system can manage very kind of tricky things, and as you can see, with many different kind of object. Actually, I can't remember the number of objects that you have here. So one of the data set that is used to train the system is the MS Coco data set, where you have I can't remember, I think it's 100 different objects. Okay. Actually, when you try it, because you can download this kind of algorithm now, and just to test and to produce, like one of the famous one from this team is called the deep mask. It doesn't work so well as it seems in that picture. Okay, so you can have some disappointment when you are just running the algorithm. Okay, still have some work to do to get to get more robust on different kind of configuration, of different type of images, illumination, and so on. All right? Okay. So if there is no question about this is image segmentation or detection. I'm going to continue with another point that is one of the I would say one of the trendy things of the moment. Okay. That is how to combine more deeply, vision and language, okay? And so it's important for me, I'm going to focus just on one task for that is called the visual question answering task, okay? And to do that, I need to talk a little bit on the way that you can process the data as, for instance, the text or the audio, the sentences and things like that. So that's why before going onto the VQA visual question answering task, I'm going to talk a little bit about the sequence modeling with recurrent neural nets. Okay. Okay. So I would say in deep neuron. Deep learning, I would say that at the end of the day, we would have covered, most of the points important. I would say that the first one is really, all the things presented by Eduardo about perceptron, multi-layer perceptron, understanding the learning, backprop, and so on. That was really, the first thing. The second thing is really, to be used with convolutional neural net, started by Eduardo, just to really explain, when he tried to explain the invariance question, the robustness to the way that the input may change, and how to get all these kind of things and semantic levels progressively. So this is really, the second point, where also I detail some extension about the deep architecture today that we use for vision, classification, detection, segmentation, okay? Then there is a third point that is very important, is to see the extension to the RNN, so to the neural net that are recurrent and that are dedicated to process more sequential temporal data, things like that. So I'm going just to give a short overview on that. And the last one that we briefly evocated this morning is about generative system. So we don't have time during only one day, sorry about that, to go into the detail of generative system. And there are different techniques, certainly the most, how you say, buzzword at this time is the GAN. The GAN for generative adversarial net. Okay, okay, but okay, next time. Okay, so just to figure out and to summarize why it's important to see also some other kind of neural net at this time, as presented this morning, perceptron, okay, on multi-layer perceptron. Okay, as mentioned, is feed-forward system, so you go straight from the input to the output. There is no feedback and so on. Okay, and the ConvNet is the same. It's a new kind, it's a new architecture, but it's exactly the same kind of things. Okay, and then for the training, it's straightforward also, as explained this morning. When you want to learn this kind of things, okay, you go through the model. You have an output. For each output, you have a label, then you have a loss, you have the error, and thanks to the error, you go through the backpropagation, okay, started from the top and going through all the layers of your deep. Okay, that's clear. And then, yes, most of the time, I think it's good to recall also, it's as mentioned and deeply explained by Eduardo, but okay, you can do it if you want, just compute one error for the whole set, if you want. Okay, this is the error is just the sum of the error for the whole data set, and then you have an error. Okay, this is your global error. You compute the gradient for that error, and you do one update of your system. Okay. But basically, the problem, of course, is that if you have 1 million images, you go from 1 million, you adapt one time, okay? It's and if you need to do, I don't know, 10,000 of update to get the right decision, okay? You understand that, so that means you need to do 10,000 of times passing 1 million of images, okay? So it's a little bit crazy, and it's completely, I mean, like inefficient way to learn, okay? That's why it's quite better to do some kind of stochastic gradient descent as presented this morning by Eduardo. So that's why you no more wait to process all the image into the deep to do an update. You do update eventually for each image. So you pass through an image, you complete the loss, and you go and you do an update of the gradient, okay? This is the math is very clear. It corresponds to a stochastic gradient descent, right? Okay. Of course, it's absolutely not the good way to do. Okay, and we know that there is some kind of trade-off in between the two extreme things that I just presented, and the things is that you are going to compute one update for a small set of images. Okay. So that means you are going to compute, I mean, like one gradient update for 100 of images or 10 images or something like that. Okay? Okay. Okay, so from that, so the question could be, right, okay, up to now, we are able to process static images, okay, or static data. You have one input. This morning it was first a vector, then after a matrix of, let's say, a square matrix, let's say one image as input, okay? The question is, for instance, is it possible to extend the techniques to video, okay? And how can we do that? Naive strategy, okay, first, okay, you say, you take you consider your video, okay, as a set of still images, right? Okay, so you have like a big set of images, and let's say you forget the order, so you forget that it is a sequence, but you just extract for each of them the decision, so you present each image, each frame of the sequence to the deep. You have like a certain number of decisions. So it is a video of that. You just aggregate, you take the max at the end, okay? You take the final decision from all the frame decision, okay? So for instance, you average, okay? So you do an average pooling, so that means you average all the feature vector or all the decision, or it depends on the way that you want to do that, okay? But as you notice, certainly, we completely give up the temporal information. Okay, as I say, we consider as no order into my sequence. I just take all of them and I pool the decision together on average pooling or whatever. Okay, so it's not certainly the best way. I mean, because there are a lot of information inside my temporal information inside my sequence, okay? So it could be a question on how we can get benefit of that, okay? A second example is, for instance, sentiment classification thanks to analyze of sentences, okay, for recommendation techniques, for instance, for system. Okay, so in that case, the input could be, for instance, okay, at first exciting, but overly sentimental. Okay, and the output should be like I want to give a bad review for that. Okay, it could be somehow reviews for movies and so on. Okay, so I take a lot of sentences or comments given by different users, and I try to then to extract some automatic way. I mean to classify and to have the right recommendation for any kind of movies. All right. So the classical, for instance, the basic NLP strategy for that would be to have some vocabulary, to count appearance for that, to train a shallow model, etc., and to give the score. And then I will obtain something that I'll try to accumulate, exciting, plus sentimental, plus overlay, etc. And then, again, it's just a pooling, like a sum pooling of the elementary decision, okay? And anyway, it's not straightforward in that case, again, to have like some temporal structure over there, okay? So one way to get advantage of the sequential data is to consider some more complex system that I'm going to explain now. Okay, so on this example, for instance, you are still on the classical strategy. You start, for instance, for a word. It can be also for character by character. I mean, I just show here, I mean, like a splitting of my sequence by character or a splitting by word, okay? It doesn't matter for what we have. We have this kind of encoding on a dictionary, okay, a basic dictionary, whatever this kind of things. And then, after, I'm going to consider that this sequence, okay, has a certain order, and then I'm going to consider a structure, okay, that take into account one thing. So, for instance, the current word, okay, and I go into a system that have inside his representation, I mean, like the information coming from the word before or the state before, okay. And the way to represent this information is to have this kind of recurrent connection into my system. So instead of having a dip, okay, as I presented before, imagine you have like a feed-forward dip, okay, you have another thing, okay, a neural net, okay, but there is like a recurrent connection here, and that means that is connected to the time before. Okay, it can be before or on the right, on the left, or whatever you want. Okay, and so this is okay one way to represent this kind of recurrent neural net. The other way is when you just open and represent the things for t plus 1 or t plus 1. Okay, and so for the sequence between t plus 1, in that case, you are going to have this kind of model, still have the one input at step t, okay, at time t, okay, and this input is going to the system, okay, that also has some knowledge, internal knowledge, that is usually represented by also a state, okay? Internal state that is usually represented by h, okay? A h function. So this function is also depending on t, and then here it's ht, okay? And from both of them, okay, you are able to actually to produce, okay, some kind of, not output, but some kind of the next internal state, okay? So what does it mean? It means that you know something, and thanks to this new output that you observe at the moment, you are going to improve your knowledge of the things, or to modify your internal states for the next step, okay? And of course, you also are able to produce the current output that the system will be asking to produce, right? So in that case, summarize, you have one input, x, as before. That can be, for instance, the current word, okay? Okay, you are going through a system, and you express the things with the word that you give before, okay? So the input-output representation here is also say that it can be a vector, okay? So it's a function, but that can be expressed as a vector depending on t, okay? For the dimension, and this more or less something that, of course, has some memory about the past. Okay, that's why it's called memory of the model. That can be short-term or long-term memory. We can discuss about that, right? Okay, and then, of course, I'm going to shortly describe how we can learn also this kind of system by backprop and so on, right? Okay, just if on the example, so what does it mean on the example I was presented before? So at first exciting, but over sentimental, how we can encode this kind of system or this kind of sequence into a deep RNN. In that case, it can be, I mean, like this is the first, so this is x at the time 0, okay? And eventually you have an initialization that can be, for instance, 0 for your internal system. You produce an output, okay? And in that case, the output that we want to have for the system is a score. Okay, that can be, of course, a negative score, a very negative score if it's a bad review, very positive score if I want to give a good review, a nice review for this movie. Okay, but I can analyze, I mean, of course, each time, what is the output, what is the current output, okay? But at the end of the day, what is interesting for me is to produce the output once I have seen and processed the whole sequence, okay? So the main output for me, that's why I put this here, okay? It's that one, okay? So I can have a look on this kind of intermediate output, okay? But the real output of my system when I'm going to process a new sentence that tell me something about express some feeling about one movie from one people, okay? What I want my system give me is the final score, okay, from that sequence. So he has to understand from my sentence if I think that, if I would recommend this movie or not, okay? So he has to translate my natural language expression, okay, my sentence, into like a feeling and a score about the movie, right? And so as you see, I try, it's like toys, but I can to express that at the beginning I don't really know, so I try to, first exciting, certainly if I would stop here, certainly it would be something like quite positive, okay? See, if my sentence stopped here, I would produce like a good score, okay? Because I just see something like, it's first exciting, and that's all. Okay, it seems good, okay? But of course, when I continue and I go into this kind of things, of course, the score will be updated, and the whole thing is that this final score coming with the internal state here is taking to try to, to having like understood all the seconds, all the processing of the seconds, so the word after word, okay? So you see that in that case, it's really take into account of the order that the words are processed into my system, okay? So actually it can do that. It can do that, and it does. Okay? So just a summary, okay? I recall that we have nothing about just feed-forward system at the beginning, okay? It's not, okay, very well adapted for, as well for video or text as soon as we want to really, take into account of some temporal or some sequential information, I would say. And with RNN, okay, we can do that, and so we have to go into the detail of this kind of system now, okay? Just to show the different kind of architecture that you can have, okay? So here I present four kind of sequence modeling that you can consider. I will show after a few things about training, okay? And also some one or two typical vanilla architecture that we use for doing this kind of task, okay? All right, so the different type of things that we can have is one-to-many, okay? The idea is, when I say one-to-many, it means one input to many output, okay? Many input to one output, okay? This is typically, the things I just presented before. Many inputs, a whole sentence, and one output, the score, okay? I can have many-to-many and many-to-many parallel. I'm going to, just to give few examples on that. So, for instance, okay, the example before, it's exactly a many-to-one, okay, sentiment classification. I'm just interested in having one score as the output, okay? But as the input, you can have as many terms, okay? So here I consider the decomposition with word by word, okay? But you can also go through decomposition character by character if you want, okay? And then the sequence is really, like the sequence of the different character up to the end of the sentence. Okay? So, another many-to-one, more complex, okay? This is exactly the famous VQA task that I'm going to detail after that, is many-to-one. Why? Because you have complicated input that is even more than 1 second, but you still have 1 second, so you need to transform 1 second plus one image, okay, somewhere, and to have an answer that is very, like yes or no, for instance, here, or just a classification, okay? So again, it's a many-to-one here, okay? And basically, it could be represent the things I presented before, as the input like that, with the seconds, with the RNN here, okay, and to model all the text information, okay, and then I also use a deep net to model all my image information. Then I merge them together, and I obtain the output, okay. Another one-to-many. Okay, very fun for image, and it's a one step. It's a one way to go further than just for one image to give some keywords. Okay, sometimes it's boring to say, okay, the only things that I'm able to give you for one image is that a car, bicycle, or cat. Okay, we can go one step further by saying, okay, I have one image, for instance, this image, okay, and my output is that one, okay. So it's a cute little dog sitting in a herd drawn on a sandy beach, okay. So one input, one image, okay. Many output, many in terms of many words, because I want to generate a sentence, all right, okay. And so basically for that, you see here training set. So you have many images where I give you the image and the sentence. Okay? And I ask the system to learn, to analyze the image, and to be able to produce and to generate a sentence. Okay? And typically, this is exactly an automatic down captioning for that. Okay? It has been proposed typically. One of the first team was the Google Print team to do that. Okay? Then really, I mean, like you put as an input to the system that image, and the system is able to produce exactly that sentence. A dog is sitting on the beach next to a dog. Okay? Still boring, but it's better than just saying two dogs, for instance. Okay? All right. And so how we can model that in terms of recurrent neural net, so in terms of deep, which kind of deep we can put to just to be able to model that. Okay, there are two ways to model, or I mean, certainly more, but the first thing is that to put the image every time as the input of the RNN, okay, plus, okay, some initial states, and to ask the RNN to be able to produce the sequence, okay, thanks to that, okay. So that means when you produce the image and you have this output, in the same time, you produce something like, say, I keep in mind that I already put a, so perhaps a is not very, but okay, a dog here. So I keep in mind here that I already say that there is a dog, okay? And when I see the image, I try to characterize how is my dog. So we try to understand these kind of things, okay? I already produce a dog, and then I'm able to say standing, sit down, I don't know, behind, or things like that. Okay, so it's typically the kind of things that the system tries to learn. All right? Yes, and the other way, okay, so actually it's your choice how you can learn this kind of system and what you put inside the system and how you define. And there are different ways to define the input-output, okay, to represent the same problem. Okay, so the other way that have been proposed also recently was, I mean, like, I use my sequence, okay, of course this is during the training, okay, I use my sequence here that I know that is good and the image, okay, but if I am then during the test, okay, what I'm going to do is that I only have the image and I just put the, okay, start the things, okay, then I generate a new state, of course, for him, and I generate one character, my first word, okay, and this word will be used, okay, by you as the new input for the next thing, okay, and so that means actually you use the current output of your system, okay, to how do you say as a new input, okay, to the same system, and you only present one time the image in that case. Yeah, sorry. It's a way. I mean, the way that is merged them inside the RNN really depends on the type of RNN you are considering. But basically, in that architecture, okay, and it's different from the previous one, okay, you only present one time at the beginning of at the time 0 of your RNN, you present your image, okay? But of course, your image will be always encoded into the internal state of the system, okay? So, as I said at the beginning, I mean, the state, I mean, this RNN keep some information, of course, thanks to this previous hidden state. I mean, what we call the internal state of HT is there to be combined with the new input. But okay, so you can consider that the image is still there, okay? And now the image is there, the image is merged now with the A, okay? And now here it's a merging of A plus image plus dog, and etc., etc. Okay? Does it answer to the? Yeah. Okay. Okay. Okay, but yeah, I'm. It's here. It's really, I mean, like to give some example. Okay. At the moment there is no. I mean, like definitive architecture. Okay, to model this problem that is used. I mean, we are working. I mean, this is an open research problem to understand how the best way to combine the image, when, and how to get the information about the temporal efficiency of the RNN and so on. Okay. So I just present two kind of two extreme way to model the problem, just to to show you how RNN may work. Okay, right? Okay, and okay, then I'm going to switch this kind of things, but basically, of course, there is all the things when you go to the elementary, I mean, analysis of this kind of things. So you are no more interested in having what is the pen. You just try to learn how to produce anything that is text. Okay, and then the things you learn is already depending on what you pass through the system to be learned. So there were some examples about Shakespeare this morning, and this is typically, I mean, this kind of system are able, more or less, people say, to learn any kind of programs, okay? So you can imagine also to learn a LaTeX program. It's possible, I mean, and people try to do that. So to have always this kind of, to /begin, /end, any kind of things, okay? With many things in between, then this kind of character-based things may try to learn to close something when you open it before and so on. Okay? All right. So many-to-many. Also, we have this example for the many-to-many that could be interesting. Is that in that case, typically, we want to do translation. Okay? So, yeah, for people from natural language processing, of course, it's very interesting, and you know that there are like a small revolution on the ability to the system. I mean, actually, to really, I mean, translate with a very high quality in many different languages. Okay, thanks to this kind of deep learning system. All right, and basically the idea is that, as you see, I don't care about the output here, okay? So I do not even represent them, okay? I know that I have a sequence as input here, okay? So this is an input, so I don't care about producing something here. So my input is really, I mean, like the agreement, blah, 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 etc., up to the, and I stop here. And when it's finished, okay, I try to learn, I mean, the same RNN as it was like in the following, okay, of the state here is just have summarized all the information in my input sequence and is now able to start to produce an output, okay? And then at the end, and only at the end of the sequence, I ask the system to start to produce something like that, up to it decided that to stop, and it's over, okay? And so, of course, in that case, here, the character and the word that he produced will be, again, reuse at the next input for the system in order to be able to produce the whole sentence. Okay, so you see exactly here many, too many, okay, many words as input, many words as output, okay? And the way that, okay, people connect them together is just here, okay? During the training, I know that, and during the training, I know also that, okay? So that means, okay, I give that to my RNN, he does something, and thanks to the internal state that he has here, and that, he should be able to produce a first word, okay? And as I know the word that he should produce, I can define a loss and penalize the system if he made a mistake, okay? So here, you see that we can have loss at different level, okay, as soon as you have, we have this information available during the training, okay? So the training is working like that. And then, of course, when you are doing the test, of course, you have no more this kind of information here. So you can penalize and you use it as really, I mean, like generative sequences, okay? Generate sequences in the new language, in the target language, okay? And this is like a quite general principle that you can adapt also not only for text, but also for any kind of inputs, in sequences as input. And for instance, audio, if you want to do some machine translation from audio, some speech to text, it's possible to have the same kind of recurrent neural net architectures. Okay, so I remember during the discussion, during the break, that many of you have a lot of very complicated sequences to process, and I think this is one way to do that. Okay? Okay, all right, so yes, to summarize, so we give some example on one to many, many to one, many to many, that can be in parallel or not, okay? And so you can really adapt this kind of things to many, I mean, many kind, just using this kind of RNN framework. Okay. So of course, one question is that is it possible to derive the kind of beautiful framework presented by Eduardo this morning on gradient-based, stochastic gradient-based, and backpropagation into the system? Because of course, as presented this morning, their systems are also huge, okay, have also a very large number of parameters, and usually also are trained with huge amount of data. And that's why also because, for instance, I mean, because we can find very large corpus of data that are already annotated, okay? That's true for text, to represent the text, even for translation. We already have a very, very large corpus aligned for this kind of task. Not for every language, but of course for some of them. Okay? So, okay, I'm going to just to skip that, just to give, I mean, the main point of how we can go through this learning, okay? So let me give very, I mean, like, if I want to have like the vanilla RNN, okay? So how it is inside, it can be something like very, very, very simple like that, okay? So it's just from the input, just like a projection, something like a linear transformation, right? So here you have a matrix from the input to the intern state, okay? But to compute, of course, the intern state that should depend also of the previous state, you combine this with another transformation operate on the previous state, okay? So that means that the way to define the internal state is coming from two transformations that you try to learn, okay, of course, and this is really, I mean, like these two matrices at the parameter of the system, okay, that give you the current state of your system, okay, and with the next, if you are trying to compute the t+1 states thanks to the t state. All right? And it can be the state for the output. Okay, here you are still inside. Okay, and you can decide that just to go outside to produce one output could be, in that case, just to have this kind of linear transformation from, okay, my, of course, updated state. Okay, with bias or things like that. Okay, so even simpler things. Okay, I think all the coefficients, and you see, thanks to this kind of things, I am able to, for instance, to compute the sum of the input. Okay, so very simple, totally trivial things. Okay, you just say, okay, you start with 2. Okay, basically the sum is initialized to 0. Okay, and inside, so the RNN, you consider this. So that means the internal state will be update 2. Of course, the output state is equal to the internal, so it's 2 also. When you arrive with a new input, you exactly do the sum here. Okay, so your new internal state, etc., etc. Okay. Okay, so you can do some more tricky things, but just considering instead of one scalar input, for instance, a vector with 2 inputs, and you can decide that what is exactly to compute this if the sum is greater than of each, yes, I think of each component. So you want to determine is the sum of the value of the first dimension, okay, when you accumulate this first dimension, okay, is greater than the second one, okay. And so, of course, it depends on each time it can change, okay. And the output here is just tell me if it's true or not that the first is greater than the second component, okay. So typically here is 2 is greater than -2. Okay, then I should have something like 1 or big as the output. Or here I just decided that my output to be 5 times the internal states. Okay, that already represents something that should be positive if it's greater and negative otherwise. Okay. And so at the beginning that is very true and strong, and after I take, and so I have to accumulate with a new sum, and so it's no more very true, and you see if you count everything, you will see that after 3, because here I add many different things at the second one, okay, it's no more true, okay? So I need to have like an output that is close to 0 or eventually even negative, okay, if I want to take into account of this kind of thing. All right, but this is basic, just to show you that you can accumulate the information into the internal state and then to produce different output thanks to this internal state taking into account the past, okay? And of course, for the loss, because the idea here is how we can train this kind of system, okay? In that case, you can compute, I mean, the loss in between every predicted value, okay, for the target here. And the idea here of the loss is that if you know that it's true that the sum is positive or not, I mean, the sum of the first and compared to the second. And then if it's true, you can decide that you should have 1 as answer. And if it's not true, actually here, okay, it's not negative value, except it's a 0 value, okay? Actually, it really depends on the way that you model your things. And in that case, of course, it's very positive. It's close to 1. And when it's very wrong, so very negative, it's close to 0. Okay? Okay, and the good thing is that you can accumulate and you can backpropagate through the different part of what we call here the unfolded RNN. Okay? So unfolding is really when you express each time of the RNN. Okay? And this is very important, and this is one point, and this is very important for the learning. When it is unfold, so that means that it seems that you have several RNN here. No, it's not true. It's the same RNN. So that means that all the parameters, the internal parameters, are shared, are the same. Of course, the internal state is updated, and so internal state, of course, is not the same You have a production rule, okay? T plus 1 depends on T, but is not independent from T, okay? But the parameters, the value matrices I mentioned before, are all the same, okay? That's why it's unfold, but it's not different RNN, okay? And this is, I mean, certainly the main difference with the classical feed-forward system, okay, where we have only one way to backpropagate the information, okay? In the feed-forward, okay, you start on the top and you go through the deep and it's over, okay? As you see here, it can be, it depends on the way that you model, but the idea is that perhaps I can go from the last one and I can derive like this, but as you see, I can also derive a loss here and a loss here and so on, okay? And so that means that during the training, I have to pay attention about the way that I backpropagate the information, okay? Just to be sure that I update correctly, my RNN system. So I have to update my W, okay? So my vector, and I have for this updating to take into account where I am into the system and eventually to average two gradient coming from a different branch of my system for one state, one current state that I consider. Okay? And then you accumulate and you do that and you backpropagate and so you still have, you have one more constraint that in a classical way is to pay attention about where you are inside the temporal processing. All right, so there are many ways to define, and as I said, there is not only one way even to learn, okay, this kind of system. You can eventually decide that you pass through all or not, or if you reconnect one input to the next input or not, or one output to the next input or not, and so on. And so, okay, it gives you some advantage in one case and some drawback in the on the other, but okay. All right. So another example that when I mentioned some sequences, so I go through that, and then at the end of my sequence, I start to produce the output, okay, exactly as I mentioned for the translation before. And that's why, actually, I just express my loss thanks to the output that I know, okay? I don't go through other things that I could have before, okay? But thanks to all of them, I will go up to this, this backpropagation, all right? So I not, again, repeat what Eduardo explained this morning about gradient vanishing, but you can imagine that as you unfold your system as many times as you have many terms in the output and in the input, you can imagine that the sequences that you process and then the backpropagation step are bigger than in a traditional feed-forward deep learning system, okay? And then this kind of vanishing gradient or exploding gradient and things like that make this is a maze is a big issue for this problem. And also as mentioned, Eduardo, if it works, it's because we have some techniques that for well-defined architecture, well initialized, well normalized, well, etc., we get some solution, okay? Okay, let me certainly switch to the last part. Just give, okay, I explained one vanilla at the most, elementary, okay, RNN. Let's say that certainly the star of at this time today, okay, is called the gated recurrent unit. Actually, there is two stars. This is that one or LSTM. I would say that even LSTM are most known. I don't know if some of you know this term, okay? This one is perhaps quite less famous, but actually it should be because it's easier to train and the results are at least as good as with LSTM, okay? And typically, I just go into that one just to explain one of the idea of that one is that there are some limitations of the RNN that have been pointed out by some researchers, is that it's difficult to keep a long-term memory, okay? So what does it mean? It means like if I have a long sequence, a long sentence, okay, as input, for instance, when I see the internal state after processing, I mean, like say the 20 words of my sequences, okay, it's very difficult for the system to keep in mind what happened at the beginning of the sequence, okay? He is able to well process something like thinking about 2 or 3 times before, but learning something that can happen in many times before, it's much more difficult for him, okay? And there's 2 architecture, the GRU and the LSTM, try to correct, to fix that problem, okay? And how they do that, actually, they introduce a second, like some kind of tricky things as new internal state that is called typically here the reset gate vector, okay? And then you have 2 new intermediate states that is called the update gate vector and the reset gate vector. And your H, that is the internal state, okay, will be a dot internal product, sorry, okay, so a term-by-term product of these 2 vectors, all right? Plus, let me remember, okay, what is that? Yes, exactly, okay. Of this vector plus a term-by-term product with, okay, the 1 minus z value and something related to the combination of my input and the, as you say here, the previous state. Okay. Just to figure out what happened when you use this kind of very tricky, I mean, combination, just very basic, I mean, 2 extreme cases, okay? The one where, I mean, the update gate z is equal to 1, okay? So that means this disappears, okay? And so that means exactly your internal state, oh, sorry. Your internal state, okay, your new state is exactly equal to the one before. So you find again something like a skip connection. You remember that we presented in the very big ResNet architecture, okay? Actually, the idea of even of ResNet coming from this kind of, oh my gosh, of exactly this kind of skip connection, okay? Where you authorize the system, H, to pass exactly the identity, I mean the same H to the next one, okay? And this is controlled by this Z value, okay, like it's like a gate value. And when the gate is 0, this is the opposite, okay, you say, oh, don't, now you forget, and you just concentrate here on this term, okay? That combine actually exactly, I would say as before, as a vanilla, okay? Coarsely speaking, all right, okay? Actually, it's a little bit more complicated, but because you also have the reset gate, but okay. Basically, the idea is to authorize the system to pass, okay, through the internal to the next one. And thanks to that, exactly as before, and thanks to that, you can imagine that when you backpropagate the gradient, okay, you know that you always have a path, except when it's really noon, but okay, you have a path to propagate the gradient, okay? All right, so, okay, that was for the basic architecture, okay? So vanilla RNN, you can process seconds. If you want to be very fine in terms of keeping some long-term memory, you can do a GRU or LSTM, okay? And then, of course, you can combine that architecture like a block, exactly as for the deep. You can consider that you have like some block with CNN, CNN pooling, etc. And you repeat this kind of blocks, okay? And you can do that with RNN. So the idea is that you can stack one RNN to another, okay? And of course, you can stack really, I mean, like a basic thing, or you can have some, you can add some first a linear, then a RNN with some combination here and with a linear, or some with more tricky things. Something. It depends. It's really, you can combine. This is your choice. I mean, now different piece of deep RNN. Okay. And one way that is yes very used in the literature is just to combine actually two RNN. That the one going in one sense. Okay, the first one. You start with the sequence. You read your sequence in from left to right, okay? And in parallel, you do the same. You train, okay? You see it's in parallel because you don't care about the first. Oh, my gosh. Wait, where I am? Okay. Sorry. Okay. Then it's exactly as you have one RNN from left to right, one RNN from right to left, okay? And then after you combine them together, okay? So you can combine just the output, or you can try to combine all the different internal states, okay? So it's just what is mentioned here, where you concatenate the output of the AR1 with that one, okay? So you, of course, you just need to align the length of the sequence to be able to have something that is perfectly aligned for the concatenation. All right? Okay. So do what you want. All right. Okay. So now we are ready to go onto the last part. Okay. So it's much more, I mean, like a piece of research work here than a courses, okay? This is really an opening for different questions, and some of the questions that are very, I mean, like hot topic in computer vision at the moment. And I want to present one of the answers that we have done in my team, yes, with two of my current PhD students. I mean, the one I just mentioned before, that is one very, I mean, smart people, Rémi Cadenne, for making working all this kind of RNN system. And the other one that is Eddie Ben-Younes, that is really involved in this kind of merging information. Okay, so I'm going to see. But why it's important? Let me just do. Okay, just I'm going back to that, but I just want to recall you. Yeah, the famous mutant or question that we have here. Okay, is just to say that what I presented before. Okay, the half an hour that I take to explain RNN, okay, is this part, okay? You remember the group, okay? It's to be able, from one sentence, that is here a question, okay, to represent that question in a very efficient way as a vector. This is exactly the output of my recurrent neural net that analyze, of course, each word and exactly the sequence of this word, okay, constituting my whole question that I have here, okay? So all I explained before is to be able to produce a very nice, useful vector for actually to embed the text and the question information, all right? All the things that we have presenting this morning and up to the beginning of my talk with the ResNet at the beginning of this afternoon is to be able to produce, okay, this big vector also that characterize in a very semantic way the content of the image. All right? Okay? And now the question is of course here, is how to merge both information in order to get the right answer. Okay? So let me to come back to this task. Okay? What is expected with this kind of visual query answering system? Visual question answering system, sorry. It's really, this is, I mean, a completely absurd data set. Huh? The first one proposed by the community was completely, I mean, like crazy. And okay, we modify in the second, the VQE2, try to correct, I mean, and try to propose some question on an answer that makes sense, I would say. Okay, so you can imagine here that you have as input how many slices of pizza are there. Okay, so I don't know what could be your answer, please. 6, 7, 4, 5. No, okay. Okay, I think if I really zoom and if I reason, as Eduardo liked to do, I mean, I try to see how the lines are, and I try to find something that really not very clear inside the picture, but we could expect that there is something. And so just to say that certainly it has been already cut in 6, okay, because we see exactly, I mean, like composing the different here part that we have. But okay, but let's say that it doesn't make any sense, okay? So, but even if you try to consider some more consistent question that I will mention after, for instance, if the guy has some glasses, or what is behind the person, or things like that, you see that it's very, I mean, like interesting cooperation that we can think about between visual information and textual information inside the question, okay? And so it's very, I mean, like interesting and how we can put some reasoning, but again, because we are deep learning guys, okay, we don't want to do top-down reasoning. We want to try to make the thing by learning, but emerging with a very smart architecture, try to learn, okay, the things from the data also, okay? So to give enough structure of the problem, okay, but to be learned also in a very efficient way on a huge amount of data with deep architecture, okay? So as I said, of course, it's very complex and certainly needs to integrate some things about reasoning on the data, because you can imagine that, okay, for the same image, depending on the question, you will expect different answer, okay? All right, okay. And well, of course, this is not just to excite and to have new tasks for researchers, okay? It's also, there are a lot of challenges, industrial challenges, and one of them is to be able to interact, to have natural interaction also with the machine, and for instance, for blind people, okay? But not only, sometimes you are very busy, you know, you need to have some information about one image that you are not able to look at, but you want to ask many questions about that to the computer, okay? So you can imagine, I mean, it's really like a type of many kind of multimodal inputs that you can have to handle for a deep, okay? So, okay, as I already mentioned, I mean, a part of the system, the heart of the system is how you merge the information together, okay? Of course, first, having like deep architecture to well represent in a very efficient way each modality, okay? But then after, work a lot to try to understand how the question may, for instance, bias the analysis that you do on the image, Okay, so what I mean here by the bias is that you see this is the same image, but depending on the question, okay, you would expect perhaps in your system to be able to focus on different parts of the image, okay, in order to be able to produce the right answer, okay? So what does it mean? It means if the question is what is sitting on the desk in front of the boys, okay, then it could be good. And here you see again like a heat map that we produce with our system at one moment inside the architecture, okay? And it's just to see that our system tried to focus, to understand, thanks to this question, okay? You can imagine that it biases the analysis that we try to do, visual analysis, okay? And not try to give a whole interpretation, global interpretation of the image, but try to produce an interpretation by looking where the question seems to orient us, okay? To make the direction where the question seems to focus on, okay? And in that case, thanks to this kind of, so that means I remove the rest of the image eventually, okay? And from to that, I try to interpret and to say, okay, there is a laptop there, right? You can imagine this kind of behavior. And with the same image, if the question is, oh, please try, what is on the shelves in the background, okay? We would expect, and this is real, I mean like real heat maps that our system produce, to be able to focus not on the foreground, but on the background, okay? And thanks to this, really, I mean like, I try to pay attention to make an attentional system that really, I mean like, concentrate the interpretation on the back, then is able to produce the right, what is there, books, okay? All right, so, okay, we call that mutant, I can't remember why, but it's like, it's, yes, of course. It has mutant powers for the recognition, but also it's something like multimodal tensor analysis network or something like that, okay? All right. Okay, so if you try to model the relation between the input and the output, okay, we can model the things like that. Q for the query here, V, okay, for the visual information, and then the idea in the classical probabilistic framework is to be able to produce the conditional variable A, that is the output, knowing the input, okay? And we can have this kind of probabilistic framework and try, of course, to decide the right answer is the one that maximizes the likelihood in that case, all right? Okay, so, okay. This is just something, but because it's quite more general than just text and image. Is when you try to merge two different modalities, okay? I just mentioned that you can do that by basic concatenation and then you combine, for instance, in a linear way, okay? Of course, otherwise you can decide that you have to learn some linear combination, but independent for both modalities, okay? You can start to have something that is not linear into each components, but try to merge them together with the Adama product. That means component by component. And usually, I have to mention that it works very well. Okay, this is one of my favorite, and it's a very easy, of course, merge. Okay, and very. Not costly because you don't have many things to do, okay? So this is an element-wise product. And of course, you can do a multi-layer perceptron, okay? So this could be, I mean, like the basic neural net guys that say to you, okay, give me your two inputs, I put everything into a deep, and I learn everything, okay? And of course, we did that, and it doesn't work so well, okay? It doesn't even work as well as this kind of things, okay? So of course there are plenty of reasons. One of the reasons certainly is also because of the complexity of the task. You would need to have like a deep perceptron to really well represent the final function that you attempt to model, okay? And in that case, you certainly would need to have a huge amount of data to be able to correctly learn this function, okay? And when I said a huge amount is quite much more than 1 million, okay? Because it's exactly the number that we have at the moment. So it's certainly tons of milliards or billions of example labeled in order to get some answer. So I don't say that there is no solution, but okay, at the moment it's far to be the best, and we still need to do, I mean, a fine job, okay, and to find the solution. All right, and one way, okay, so that is very common for signal processing guy is to put the things into like a bilinear model. Okay, so instead of linear, you go through just a more complicated model that is bilinear. So it's linear, but considering combination of your different inputs. Okay? So this kind of model may be represented in a very, short way, like a tensor framework. Okay? And the order of your tensor is depending on the number of dimension of the input. And in that case, it's simple because you have two different inputs, okay, and one output. So you have like a cube for that tensor, okay? So 3 dimensions, okay? 2 inputs in 1 output. All right, and it's a very efficient way also for image classification that won some competition for, usually combined with deep, but for fine-grained classification and so on, okay? But there are still, of course, one problem if you say, okay, Mathieu, I take my, for instance, 2,000 vector for one image, 2,000 vector, the dimension for to represent my question, okay? And I have 2,000 dimension as output, okay? So I mean my